Hello, on behalf of the Spectrum Scale user group, welcome to our next Spectrum Scale expert talk. This one is on persistent storage for Kubernetes and OpenShift environments. I'm Bill Anderson, a member of the Spectrum Scale user group, and I'll be your host for this meeting. So yeah, we want to welcome you to this and other digital events we have. There's a couple of URLs you can click on to gather more information, as well as look at videos and information about past talks. Yeah, a little bit about our user group. It's independent. However, we work with IBM to co-develop events. It's not a replacement for opening a PMR or bug report. Rather, we're an email and Slack community and you can join us using this URL here. We host events at supercomputing, and some of these we've been doing online webinars this year because of the pandemic. So we're kind of a community for Spectrum Scale users to share information and help each other out. So we are Simon Thompson from the UK, Christy Callback-Rose from the USA, Bob Osterlin from the USA, myself, and Chris from Australia. We're essentially the board members for this user group. Yeah, and here's a URL to obtain information about our past talks. We've had 5, and today will be number 6, and we have a few coming up as well. Our speakers today are Simon Thompson from the University of Birmingham, Smita Raut from IBM India, Rana Grunenberg from HUK Coburg, and Harold Sipe from IBM Germany. And so with that, I'll turn it over to our first speaker. And please feel free to use the chat to submit any questions you have, and panelists or the speakers will respond throughout the webinar.
So I'm Simon Thompson. I work at the University of Birmingham in the UK, and I'm a research computing infrastructure architect. And I'm going to talk a little bit about what we'd like to do with Spectrum Scale and containers. So I work within advanced research computing, and we have a facility called BEAR, which is the Birmingham Environment for Academic Research. So we do supercomputing, HPC, we have AI systems, high-speed storage, high-speed networking in there as well. And we provide services right across the university. So I'm going to talk a little bit about what we want to do for some of our researchers. So they want kind of play worlds where they can develop their code. They might want to develop systems. Sometimes they're building kind of web applications to interface into their data to make their services accessible to the world. They want access to all of their data from their desktops, from on the supercomputing systems inside our sort of cloud, these kind of research environments they're building. They want root on their boxes to install software and do things. So what we do provide now is we provide VMs with NFS. The NFS, although we have some quite powerful NFS servers, it's kind of slow getting access into their data. If they've got large amounts of small files or anything like that, it has a big impact on our kind of NFS servers. It's actually quite tricky for us to manage giving people root inside those environments. So what we really end up doing is providing a bunch of VMs where we then export storage into that. But we end up managing quite a lot of the kind of software stack inside there really for them as well. And that's one of those things that we like to move away from in some cases to allow some more rapid prototyping of environments. So enter containers. This is a sort of magic unicorn. Everything's going to fix everything. They're going to give our researchers environments they can control. We want to be able to use the CSI driver to mount selected bits of our storage into the containers. We'd like to be able to give self-provisioning of containers with the storage into our researchers so that they can click a pointy, clicky, GUI thing in some sort of web tool that we're going to build to provide this. And maybe they want to do rapid prototyping of software, or they want to do some magic testing inside their systems, or they've got a new bit of software they need to try out for their equipment, so a sequencing program or something like that. And so Christopher Hall, who works in my team, and Alex Lloyd, who was a student intern who was working with us, they've done quite a lot of work on this. So I'm just kind of presenting their work really, so thanks to them. So some of the challenges we found with the sort of Spectrum Scale CSI driver, so we've had a play with it. it was a bit vague to us about if you could use existing file sets. So quite a bit of the documentation talks about, you can provision file sets in for there for kind of persistent volumes for your containers. But actually what we wanted to do was to provision the storage that we already have and push that into the kind of container world. And as it turns out, you can actually do that. But for us, it was a bit vague in the documentation. We quite like to map all of the I/O that goes on inside the container back to a single user. So if the user at the moment inside the container, they create a whole bunch of different users in there with different UIDs, that all gets written back to the storage at the back end as all those different UIDs. So when they come to access their data from the kind of outside world on their PC or on the supercomputing systems, that data might be owned by a whole mishmash of different UIDs in there. So we'd quite like to be able to do that. At the moment, I don't think we can do that with the CSI containers. There's a bunch of things that we were a bit stupid about when we were doing this. We kind of went in, it's like, oh, there's all this nice, documentation. But actually, it was a bit vague. Some of it was a bit vague to us about how it was kind of all architected. So those Kubernetes nodes, they need to be a spectrum scale client. It kind of sounds obvious when you look back at it afterwards, but it was a bit vague about where exactly that client level was running. So we have, hypervisors that are spectrum scale clients, and then we have VMs running on top of those that are Kubernetes nodes, and then we have containers inside that, which are accessing the storage. So our spectrum scale storage also provides the VM storage for those VMs. So we've got these whole layers of where do we actually need spectrum scale, and those Kubernetes kind of worker nodes. So not on the manager nodes, but on all those worker nodes, they had to have, the spectrum scale client installed on them. And the way we deployed Kubernetes didn't really kind of lend itself to us to doing that. So we tried a bunch of different networking drivers in there. Some of them caused us some trouble. There's a name mapping thing inside the spectrum scale CSI component. So if your VM name, your K8 node doesn't match the name inside the cluster, you can map it across. So because we had to add an additional network to give access to the spectrum scale storage infrastructure, they had slightly different names from the VM and the host in the spectrum scale cluster. And so we did the mapping and we thought, oh yeah, so we want to put the fully qualified domain name. But anyone who's used MMLS cluster, you'll see all of the nodes in there. And certainly in our case, sometimes we've seen fully qualified names, sometimes they're short names. I've never quite worked out why it does that in some cases. But we put the fully qualified names in. So when we were actually trying to mount persistent storage into our containers, we had a whole bunch of issues. And some of the speakers who were speaking later on actually pointed us to this and said, no, you need to have this exactly matching in there. Some other things that we kind of found as we were going along with this. So a lot of the documentation about Kubernetes talks about using Red Hat CoreOS and things like that. But obviously your Kubernetes node needs to be a CentOS or a RHEL server in there, because you need to have spectrum scale support for that. So because you have to have that client package running on there, you can't use CoreOS, you have to use one of these other ones. We also found that there's some missing default systemd dependencies in there. So when we started containers, so Kubernetes might start on reboot, we might start and try and create containers, but actually the storage underneath from the spectrum scale file system hadn't started at that point. So we had to add kind of extra bits into systemd to say, right, before you start these Kubernetes services, we want to mount these spectrum scale file systems that we've got in there. So we were using KubeSpray. So I mentioned on the previous slide, it didn't quite work with the way we want to deploy things. So we were using KubeSpray to bring up and stand up environments inside OpenStack. So you point it at the OpenStack endpoints, and you tell KubeSpray, I want to have 1 manager, 2 managers, and 10 worker nodes, and that all works great to bring up the environment. Apart from the fact you then have to install the spectrum scale client and add it to your GPFS cluster, and so there's a whole bunch of kind of post-processing work that we had to do to complete those automation steps. So we don't have a fully automated pipeline at the moment because we've got some bits lacking at the moment. So that kind of idea of having a pointy-clicky GUI, so spawn a Kubernetes cluster, we're not quite there with being able to do that at the moment. And then things like if you want to do IB pass-through from our hypervisors into the VMs, those Kubernetes nodes, then we can't do live migration. So in some cases, we're stuck with using Ethernet if we want to be able to do live migration within our OpenStack infrastructure afterwards. And I mentioned some of the networking types didn't work for us as well. So we actually had a weird stage at one point where we had kind of some weird dependency where the VM, the Kubernetes worker node, needed Kubernetes up. to be able to connect to the Kubernetes cluster to start the kind of internal DNS processing. But it couldn't do that when you rebooted the node because Kubernetes wasn't up, so you can't start the services to actually talk to the DNS. So that kind of, sent us down a whole rabbit hole of trying to fix things that were actually nothing to do with the Spectrum Scale CSI driver. But it's just, this is one of the things that we found as we were working our way through this. I think that's the last of my slides, so I'll hand back over. So I can see somebody asked a question about what networking types were not working. So I think we were using flannel networking, and that brings up these kind of VTEP interfaces between the nodes. And it was actually that component we were having trouble with. And also quite a lot of documentation kind of assumes that you have sort of ingress controllers in there. So all of your Kubernetes nodes are in some magic network that can't talk to the outside world. So when you're looking at sort of sample environments like that, those ingress controllers sort of sit in front of all those things, and your Kubernetes nodes don't normally talk to any of the rest of the world. Now, obviously, when you have a Spectrum Scale cluster, you need to be able to talk to your Spectrum Scale storage and any other nodes that are in multi-clusters. So because we're providing storage into our HPC infrastructure and into protocol services, everything has to be able to talk underneath there. So we have to have connected networks in there. Okay, I think, is there any more questions? No, there's no more questions. So I'll pass over. Thanks.
Hello, everyone. This is Meeta Raut. I am the architect for Spectrum Scale CSI driver. And today I'll be talking about high-level architecture of CSI driver and its feature functions. So this is the standard disclaimer for the content that is following. And today's agenda is a brief introduction on the containers and how it plays with the Spectrum Scale world. Then we'll talk about Spectrum Scale CSI driver details. And then we will talk about some use cases from Renar and Herald. And as Bill mentioned, after the use cases, we will conclude with Spectrum Scale on OpenShift and some considerations on OpenShift. So just to set the baseline on why containers and what is the significance of moving to the container workloads. So if you look at the traditional applications, they are monolithic in nature. Some of the challenges that these kind of applications face are the challenges in making any change because of its tightly coupled and tightly integrated nature. Any change that you make to the application affects the entire application. You have to go through the dev and test cycle for the entire application and sometimes even re-architect the entire application. Additionally, another challenge is to scale such type of applications. You cannot scale independent components of such applications, and you have to scale it by means of monolithic replication. So as opposed to these monolithic applications, if you look at the microservices architecture, what it does is it breaks down the monolithic application into single independent components, which are deployable and manageable independently. This addresses the challenge of managing changes because you can now change one particular component and not be worried about the entire application breaking down. You can isolate your changes into one part of the application and thus manage it effectively. At the same time, it is possible to scale by microservice replication and not have to replicate the entire application itself. So some of the use cases for containers are into these kind of microservices architectures, and few other common ones are in multi-cloud. Because of its modular nature and its flexibility in scheduling and elasticity in scaling, it is very much suitable for multi-cloud kind of an environment. Also, it provides the benefit of optimized resource utilization because each component can be better controlled. It also gives us the benefit of secure isolation, multi-tenancy, etc. Another advantage or another use case for containers is DevOps, development, continuous integration, because as we have seen that making changes to these kind of applications is easier to manage, and reusing of applications and services is possible in this kind of environment. So this provides faster development cycle as well. Now, let's look at the IBM Spectrum Scale highlights. Although many of you are familiar with IBM Spectrum Scale, it is highly scalable, high performance, unified storage for files and objects, and it also provides integrated analytics capability. One of the biggest advantage of Spectrum Scale is its performance because of its parallel nature, and it's providing a scale out solution. In addition, it provides a global namespace and can serve a data lake kind of requirements through its unified storage that includes HDFS, files, as well as object storage across sites. It also provides many enterprise class features, for example, information lifecycle management that can be used for automated data placement and data tiering. It also ensures data availability, integrity, and security by means of erasure coding, replication, and providing features such as snapshots, encryption, etc. With this, let's look at what is a CSI driver and what is actually meant by persistent storage for containers. So containers initially were stateless. They were mainly used for doing some analytics, and when you destroy the container, your data is gone. So they were transient in nature. But as the container world evolved, there was a need for stateful containers. There was a need to persist the storage, and that's where this concept of persistent storage and container volumes came into picture. So typically what happens in that kind of a workflow is a user or a developer has to claim for a volume. He creates a persistent volume claim, which then picks up some storage volumes from a pool of persistent volumes. Now this PVC can then be used inside the container or a pod. Pod is a scheduling unit on a Kubernetes which schedules containers. So this PVC can then be used and mounted inside a pod, and thus can provide you storage for your containers. So some of the terminologies that we should know are Kubernetes volumes, wherein a PVC or a persistent volume claim, as we just talked about, is a request for storage by a user. So PVCs typically consume a persistent volume or a PV from a pool of volumes. Then we have dynamic provisioning that allows storage volumes to be created on demand. It's kind of a self-service provisioning. It eliminates the need for administrators to do any kind of pre-provisioning, and it can be used to dynamically create storage for your containers. At the same time, it is also possible to use an existing storage device, or you use an existing storage as volumes for your containers. This is termed as static provisioning, where the administrator has to create the storage or the PVs upfront that carry the details of your real storage. And also, this also means that administrator should know the storage requirements upfront. So this is very much suitable for the use case where you already have an existing storage and you want to run some analytics on it through your container workloads. And the last concept I want to introduce is of storage class. It provides a way for administrators to define the classification of storage. What kind of storage this volume belongs to, whether it is spectrum scale storage, if spectrum scale storage, then what file system, etc. Now let's look at the high-level architecture of the CSI driver. So in this figure, the green dotted rectangle represents a Kubernetes cluster or an OpenShift cluster. And the blue rectangle represents the Spectrum Scale cluster. So as you can see, there is an overlap between these two clusters because we need Spectrum Scale client to be installed on the all or some of the worker nodes of your Kubernetes cluster where your application needs to run. Now this is because through this Scale CSI driver, we are providing POSIX access for your containers. So some of the components or the components of CSI driver are two sidecar containers that we includes external provisioner and external attacher. Provisioner is responsible for provisioning of volumes, creating, deleting volumes, etc. Whereas attacher is responsible for mounting of volumes or attaching these volumes to the pods. Now, both provisioner and attacher, they translate the requests coming from Kubernetes to another component called Scale CSI driver. Now, as you can see, the Scale CSI driver component is deployed on all the worker nodes. This is deployed as a daemon set. So if your worker node goes down, the particular driver pod on it is garbage collected. If new worker nodes comes up, the Scale CSI driver pod is deployed on the new worker nodes as well. The administration path for Spectrum Scale from the CSI driver is through the REST API. So for all administration related activities, we use the Spectrum Scale REST API. And that's why we have the requirement to have the GUI server up and running on your Spectrum Scale. It is recommended that this GUI server is outside of your Kubernetes cluster. So as you can see, the CSI driver talks with the GUI server through REST API. And you would also see that only those pods of the CSI driver talk to the REST API where external provisioner and attacher are deployed. So external provisioner and attacher talk to the CSI driver pods on their local hosts using a socket communication. Rest of the CSI driver pods are purely essential or are purely required to provide the POSIX IO for your containers workload. We also recommend that all your NSD servers are outside of the Kubernetes server to avoid any kind of port conflict or resource crunch. So CSI is a standard specification that is implemented by the Spectrum Scale CSI driver. Any of the storage plugins who need to provide persistent storage need to implement this standard specification, and Kubernetes talks with our storage using the CSI spec. The container platforms that we support today are OpenShift and Kubernetes. And currently x86 architecture is supported. PowerNZ will come later. And the availability of the driver is made through container images hosted on Red Hat Quay and also on Operator Hub. Now there is another way also possible to provide storage from a remote cluster. So you can have your remote Spectrum Scale cluster or an ESS cluster that you want to use as your storage cluster, whereas your cluster that is part of the Kubernetes is only a client cluster. So you can do a remote cluster mount and use the CSI driver in the same way as we have seen before. Now let's talk about how the workflow goes and what kind of personas are involved. So in this deployment, this traditional scale deployment with CSI driver, we do need a storage admin to manage and configure the Spectrum Scale cluster and also to create a file system on the Spectrum Scale cluster. Once this part is done, the storage admin can just hand over the file system and cluster details to the Kubernetes admin and need not be involved in any of the containers workflow thereafter. So Kubernetes admin's responsibility is to configure and manage the Kubernetes cluster, create storage classes based on the information provided by the storage admin, and then hand over these storage classes to the cloud native user. And cloud native user purely deals with the storage classes without having any knowledge of the underlying storage system. Based on the storage classes, they can create PVCs according to their requirement and also use those PVCs inside the pods and run their applications. Now, we talked about static provisioning and dynamic provisioning in brief. So let's take a deeper dive into it. So what is static provisioning? Static provisioning is a way to provision your existing storage as volumes for your containers. And how this typically happens is that a Kubernetes admin provisions static persistent volumes in OpenShift or containers. Persistent volumes are resources that actually tell you which underlying storage you want to use and how that should be used. Once these PVs are created upfront, the cloud native user claims these volumes through persistent volume claim. So persistent volume claim is created and a volume or a PV from a pre-created pool is assigned to that persistent volume claim. This process is called as binding of the volume. As opposed to that, in dynamic provisioning, the Kubernetes admin need not create any PVs. They only need to create something called a storage class. Storage class, as we have seen, are classifications of the storage. So they just create the storage class. The admin creates the storage class and passes it over to the cloud native user, where user claims the volumes using those storage classes through persistent volume claims. This is called self-service provisioning. So as we have seen that in static provisioning, the admin needs to create a persistent volume. Persistent volume is a resource in Kubernetes, and as every other resource, it has a YAML definition. So in this YAML definition of persistent volume, you would be able to see some details like what is the driver name for this persistent volume, what is the volume handle. Volume handle actually specifies which path on your GPFS file system you want to provision as a volume for your container. Now, we also provide a utility script to generate this file for the administrator based on the details such as cluster ID, file system, etc. This file can be auto-generated. Now, once this PV is created, the user creates a persistent volume claim. This is another resource, standard resource in Kubernetes. Now, if you see the definition in persistent volume claim, here the user has only given the storage requirement. The storage requirement is 1 gig and not specified any persistent volume. What this would do is it would bound this PVC to any of the PV that satisfies this criteria of 1 gig storage. In addition, it is also possible to bind or bound to a specific persistent volume by specifying its name. So this is the step where the PVC gets bound to a volume. And once this PVC is bound, it can be used in a pod definition. On the right hand side, you can see it's a pod definition YAML file. It has details about what kind of container it is running, and in the end you can see the persistent volume claim name that is being specified, which should be used as a backend storage for this particular pod. The difference in dynamic provisioning is that a storage class is created by the admin. This storage class tells which is the provisioner to be used. In this case, it is Spectrum Scale CSI IBM.com, and additionally some parameters to be provided, like the file system under which the storage needs to be provisioned, reclaim policy, etc. Once the storage class is handed over, the user again creates the persistent volume claim. And here, in this case, the user needs to specify the storage class they want to use while creating the PVC. Based on the storage class, the volume both at the GPFS side and also the PV is automatically or dynamically created at this stage. So it is at this stage that the volume is created as well as bound. And once the volume is bound, it can then be regularly used inside the pod for providing storage for your container. Now let's look at the kind of storage classes that Spectrum Scale supports. So we support three kinds of storage classes: independent file set based provisioning, wherein when you dynamically create or when you do a dynamic provisioning, a new file set, new independent file set is created on your GPFS file system, which is then used as a storage for your containers. File set based provisioning provides advantages such as you can manage the file sets, you can set quota on it, it can honor the size of the PV that is specified. You can take snapshots and from GPFS side and do all the management activities that the file set supports. Some of the additional and optional parameters that we support are UID GID that provides the volume ownership. You can optionally specify inode limit for the file set that is being created. We also support dependent file set provisioning, wherein you need to give a parent file set name in the storage class, and rest of the parameters can remain the same as your independent file set. Now, we also support directory-based provisioning, which is termed as lightweight provisioning. This is typically used if you have a need to create a large number of persistent volumes or large number of PVCs. Spectrum Scale has a restriction on number of independent file sets that can be created, which is 1,000 at this point. But if you have a requirement of really large number of PVCs, more in 10,000s or more than thousands or in millions, then lightweight directory provisioning is the way to go for it. Here you need to give a volume directory base path, vol dir base path. This is the path that should be pre-existing on your GPFS cluster, and inside this directory, new directories are created which are provisioned as volumes. Again, we do support volume ownership using UID GID on lightweight directories as well. So with that, I will hand it over to Renar at this point.
Okay, I will explain a little bit about our use cases that we have from our big data department that we lead some years ago by myself, and now I'm already in the storage area. And here's a little bit agenda. One slide about us, use case definition, what was the requirement, some details about what we make, and the encountered problems that we have with the levels of CSI drivers, and what are the planned steps that we have in the future. Okay, next slide. Okay, where you don't know our company, we are an insurance company here in Germany. It's the biggest care insurance supplier, and we have now 12 million customers, and we are currently on the second rank in personal liability and home contents insurance. And we have all the products that the insurance company gives for the customers, and hopefully we can go forward with all these things and are very successful now in the market. Okay, next slide. Okay, what was the requirement? The colleagues from the Big Data fraction told me that they have for microservice implementation a use case or a requirement to build a self-service for a Kafka message bus system for our developers to go in it and have some experiences what feel Kafka and the producer and consumer models. And this was our requirements and already an interface to storage what Kafka require to put all the messages in the topics, and that was the main points that we have. Next slide. Okay, what you here see, you can go to the complete picture. We have a Kafka self-service GUI. The developer requests a new container that established an Kafka server with Zookeeper implemented. Too much. Okay, with Zookeeper, this is implemented on a Kubernetes cluster, and we define with the CSI interface data source and data sinks, and the developer is possible to use it to generate its own data platform for testing for main things like message bus system and establish these all with the new microservice technology. Next one. Okay, from the steps that that you see here in the files, we start beginning with local storage because the CSI driver was last year not ready, and on December we see the first implementation and start with it to use the CSI implementation from Scale. And because of the requirement to have an enterprise-ready storage system for the containers, we must establish and read-write many implementation for all the workers, and we decided to use Scale for it to establish a sharing possibility for this requirement. And what you here see, we have now the Kubernetes platform with the implemented TSI functionalities that Smita mentioned, all the components. And on the bottom side, you see a remote cluster connect to all these use cases that we now have, like storage areas for consumer bases, for recipes, for trips, for incidents in our car insurance efforts, and now we can use it all together to use in Kafka self-service with this implementation. Okay, next slide. Here's a history of the status of CSI. We came since 3 years now with the storage container implementations that IBM give us, with the Ubiquity implementation at first, and now we are on CSI and started with 1.0.0, and now we are on the version 2.0.0. Next slide. Here is the view about the current status of the Kubernetes cluster. You see on the top of the slides the manager nodes in the Kubernetes cluster for EDCT and so on, and in the middle one, the worker distributed on 2 sides, and on the bottom, 1 Ansible control node and 2 infrastructure nodes where we use the quorum functionality in Scale and attacher and provisioner distribution. And all these worker and infrastructure nodes are established about a remote cluster mount implementation from the other cluster that we use to share these file system to to this Kubernetes cluster. Next one. Okay, and some issues that we have in the implementation of all these things. During the implementation of the beta 5.5, the storage cluster was this cluster. We see some REST API changes, but it's now fixed. There's no more problem. One problem that we have are already the point. If you had a disconnected internet implementation, you have already the problem that you must push the images, and already in the YAML definition of the operator, the right images and the right sidecar containers that you see in the middle of this slide, that must already established in the definition. You can go forward to apply these YAML definitions during the installation. Account open question is the GUI HA implementation. Currently, we have only one GUI established, no second one. I know about in our ESS implementation, we have two of these GUI, but we have no load balancer currently, and wait for the containerization of the GUI. In the implementation in the past, we see in some updates already problems with the asynchronity of the KA as EDCD component, like config rule definition or secrets, and we have to put and delete and then reapply, and after that it works fine. And already the GUI node cannot be implemented on a CSI node because of port conflicts. The question here and to the development where it would be possible to change the GUI port or the port definition currently to other ports that we can already establish this. Okay, next one. And here are some steps or some blend implementation. Currently, we are in the implementation of OpenShift with CSI. The first cluster is already running since 2 days, and hopefully we can already go forward with this. I know about the GUI containerization in the next major release, and hopefully we see a complete implemented container native storage effort from the Scale side to establish an easier implementation on the Kubernetes cluster without all these things that the first speaker mentioned. Okay, that's all for me.
Well, thank you very much, Rainer. This is Harald Seibt from the EMEA Storage Competence Center. I'm working as an EMEA expert for this particular area, and I did work with quite a couple of client cases that I would like to present. So I'm going to talk about some of the use cases that I covered in the past almost 2 years right now. So if you ask me, the CSI driver is probably around since December last year. So obviously I worked on these particular scenarios even before the CSI driver was there. So we did work, for example, with an automotive client on one of these quite interesting advanced driver assistance systems projects, where the client actually needed to ingest with very high data rates, going back to what Smita mentioned. Expecting Scale obviously is one solution that is very nicely shaped to handle that workload. And obviously they also wanted to bring in containerization, especially because they are using the AI algorithms to exploit the data and to analyze the data and build their models for the self-driving cars. using Kubernetes and container technology. So for this particular client, unfortunately, I can't disclose the name. For this particular client, we used Spectrum Scale and ESS as the backing storage, built along with x86 servers, and for AI algorithm acceleration, they are using NVIDIA GPUs built into these servers. Then at that point in time when we started the project, they had VMware ESX as the kind of common layer, as the infrastructure abstraction layer for all their server infrastructure. And they decided to go with OpenStack for easy deployment and self-service creation of virtual machines, and potentially even in the future bare metal machines. So they put, at this point in time when we worked on it, OpenShift 3 on top of it, which is based on RHEL. So the VMs were RHEL. And then we had OpenShift on top of the layer. So as you can see, quite a sophisticated stack. But just to complete the picture, this infrastructure was a so-called infrastructure as code pattern. So they used Terraform to actually bring up the OpenStack cluster, for example, bring up the stuff on top. And then they used Ansible to, for example, deploy OpenShift on top of it, and also to control things like configuring a Spectrum Scale client on the nodes where Spectrum Scale needed to be placed to interact with, at that point in time, the so-called storage enabler for containers integration. As the environment kind of evolved over time, the client did reduce the complexity of the stack. So by now, they actually eliminated the VMware in between. So nowadays, OpenStack is handling all the kind of infrastructure management, software-defined networking, configuration, and the things on top of the bare metal hardware. So we got it up and running. We installed the solution that we had at that point in time for containers into their environment. There were some lessons learned, especially when you use OpenStack. You need to take care that the way they have planned their infrastructure, they did not have a dedicated network controller inside the VM. They used the so-called floating IP concept to bridge data traffic over to the Spectrum Scale cluster, which obviously gave us some headaches in installing a Scale client into such a VM. So we needed to have a dedicated NIC assigned to the VMs running the Spectrum Scale client. And then obviously we also needed to cope with the OpenStack firewall to allow the traffic to the Spectrum Scale cluster outside of these kind of cloud infrastructure. Obviously, we did not take all the available nodes to put Spectrum Scale on top of it. This is a common pattern that you will also see, for example, in OpenShift environments, where you place the Spectrum Scale workload on worker nodes rather than on master nodes. So you need to have some node labeling and designation. But that's nowadays quite common practice. At that point in time, we just started introducing this. At the end, finally, we made this solution that was in place there at this point in time, and they're still using that, just about to shift to the latest OpenShift generation. So they will eventually switch to CSI quite soon. But at the point in time, they are using this storage enabler for containers and OpenShift 3, which are now available as a documented kind of documentation and best practice. And I think the important point, and one of the most important points for the client, was what also Simon mentioned before. So the capability of Spectrum Scale and the CSI integration, and also at that point in time with the previous solution, we were able to just reuse the data that is around. So by creating Kubernetes constructs that points to the existing data. And that's both valid for the previous solution as well as for the CSI solution. So to summarize, it turned out that Spectrum Scale is a quite great fit for this data-intensive engineering, like autonomous driving, autonomous steering, but also other workloads that require both high-performance ingest, probably through other protocols like NFS, CIFS, SMB, and still allowing you to exploit new kind of application architectures in a containerized landscape and giving them access to the very same data. Plus, obviously, with this kind of data volumes that we're talking about, being able to use spectrum scale information lifecycle management is also a great benefit. Another use case that I want to briefly touch is a joint work with a cloud service provider over here in Germany. They wanted to do something similar to the previous showcase, but for their clients. So providing a sophisticated AI platform as a service to their clients. So for this particular case, we built a heterogeneous infrastructure with IBM Power as well as x86. And yeah, you might see it on the upper right-hand side. We use the kind of previous strategic solution for IBM in the container environment, which used to be IBM Cloud Private. And with this solution, we enable the client to build a very sophisticated underlying storage plane that enables the clients of the cloud provider to mix and match and pick the right storage layer. As you probably know from other public clouds like the IBM Cloud or AWS. So we define 3 different tiers and enable this cloud provider to leverage the underneath spectrum scale capabilities to mix and match and map these to the container environment. So the key requirement was this tenant isolation, obviously. So we did not go with the dynamic provisioning that Smita explained. That was also possible with the previous solution as well as the current CSI solution. But rather kind of used semi-static provisioning done by the cloud service provider, automation rather than by self-service through the client. And this allowed the cloud service provider to have a very strict control over the provisioned file sets for the clients. So they could, for example, have their very own naming schemes rather than automatically generated names, and integrate this with service levels they gave to the client, like backup capabilities and like doing snapshots on a regular basis, which they did on the spectrum scale layer underneath, transparent to the client. And as I mentioned, it got integrated with this kind of 3-tier idea of different storage classes. So underneath, obviously, we did have kind of fast SSDs as well as SAS and SATA drives for 3 tiers. And obviously, when these file sets got kind of semi-statically provisioned, we mixed that with policies, with placement policies that are available on spectrum scale. And as I mentioned, we started with this previous version, storage enabler for containers, but as a kind of one-off showcase, we've also proven that in such a particular environment, also the CSI driver works. So this is not a kind of officially IBM supported scenario over here, but for this particular client, we did build a one-off solution for IBM Power. And as Smita said, and as we discussed in the chat, obviously IBM Power will get supported with a solution combined with CSI later this year. So to summarize again, it turned out that spectrum scale in combination with the recent cloud platforms is also a quite good solution for somebody who offers cloud computing service to their clients, like internal or external clients. And we're looking forward to getting even better integration with our cloud native kind of evolvement of spectrum scale that Smita will briefly cover at the end of this session. Let's touch on another scenario that I'm currently just discussing with a big client over here in Europe. And they asked for a 2-site disaster recovery solution with the constraint to have 2 clusters, 2 Kubernetes clusters in 2 different locations, not being connected on the Kubernetes level, which is probably something that you might want to do because stretching a Kubernetes cluster can be quite sensitive, especially because of the topic that Rena also touched with regards to the backing etcd database latency. So what we kind of architected and also implemented, so everything that I cover over here, I did implement for the clients, is a way to use Spectrum Scale in a stretch cluster mode to actually tie together the Kubernetes workloads. So to be more precise and explicit, we use the showcase as a MongoDB kind of disaster recovery solution, where we are operating these clusters in an active-passive manner. So let's consider the left-hand side as the active environment and the right-hand side as the passive in case a disaster occurs. So on the left-hand side, we provisioned MongoDB and the underlying storage, and the underlying storage got provisioned in a dynamic manner, so it does not need to be static on both sides. And then we use Spectrum Scale static provisioning to expose the very same storage to a standby pod or Kubernetes application on the disaster recovery side. So whenever we get a failure on the primary side, there is just the very minimal step involved on the right-hand side to actually scale up the deployment of the MongoDB to get back operational in very quick turnaround time. Because the data is already there through the stretch cluster nature of Spectrum Scale, and we just need to ensure that the right-hand side is keeping up with the data. And then we wrote some data on the secondary side, and then tried to fail back. So we scaled down the deployment on the right-hand side, scaled up again the original primary side, and proved that obviously the new primary side sees the data that was kind of written during the downtime of the primary side on the secondary side. So this is a relevant and working scenario for disaster recovery in containerized environments. As I mentioned, etcd is quite latency sensitive, and another use case for this could also be, because also clients ask me for this one, to isolate tenants more strongly than you can do in a single Kubernetes cluster. So if you want entire kind of separation of tenants, you build two separate OpenShift clusters. Each one has its own kind of kube admin role. So there is no kind of overlap with regards to access to compute, application, and storage resources. And still, when using Spectrum Scale underneath, with the given scenario, you could potentially share common data rather than duplicating sets. So probably my last use case is covering the multi-cloud scenario. This is also what a couple of clients are asking for, especially those clients who want to share data from their on-prem environment to the public clouds. And a scenario that we built as part of the Spectrum Scale CSI Redbook that you'll find out there in the internet is a scenario where we use AFM, active file management technology, to replicate data from a on-premise home site to a cache site, for example, in the IBM Cloud or in AWS or both. So as long as you use this in a similar kind of DR case with only primarily writing to the active site, this can also be achieved in such a kind of very remote global kind of cluster setup with using public clouds. As I mentioned, we were focusing on the single writer side for simplicity reasons, mostly, and we took care that if we kind of spin up the OpenShift clusters in the remote cloud locations while the home site is going down, we could access the very same data and use the very same workload on these kind of replicated setups. It is worth to know that if you use Scale on AWS, you need to wait a couple of days right now, actually. So hopefully later this month, we will do have support for the Spectrum Scale graphical user interface on AWS, which is a prerequisite, obviously, for the CSI driver, as you learned previously. And we just also announced support for Azure through a business partner for a similar kind of scenario where you can deploy Spectrum Scale. So we are not limited to AWS or a particular cloud. So again, Spectrum Scale turns out as a quite good match for multi-cloud data plane. So being the common data plane, common namespace across clouds, and allowing you to transparently migrate or copy over data if required to a remote cloud entity. With that, let me please pass back to Smita for the concluding slides.
Okay, so in the last few slides, I would like to focus on some deployment considerations on OpenShift and challenges that are there on OpenShift while using a traditional Spectrum Scale deployment, and how we are coming up with a cloud-native Spectrum Scale solution to address those challenges and many more. So on OpenShift, as we have seen in the initial architecture diagram, there is an overlap between the OpenShift cluster and the Spectrum Scale cluster, because we need to install Spectrum Scale clients on the OpenShift worker nodes. But OpenShift by default is all Core OS, and Spectrum Scale is not supported on Core OS. So it is a requirement to have RHEL worker nodes to be attached to the OpenShift cluster, where Spectrum Scale can be installed and where CSI driver will also be installed. So this is an additional requirement that comes up on the OpenShift, and all other required nodes like the GUI nodes, the NSD nodes, if you're using protocols, AFM, etc., that have to be outside of the OpenShift cluster. But OpenShift is almost kind of moving away from RHEL. In fact, for their other architectures like Power and Z, they are not supporting addition of RHEL nodes to the OpenShift cluster. They are going to be purely Core OS. So we need a solution to work with pure Core OS deployment of OpenShift cluster as well. So that is where what comes into picture is containerized Spectrum Scale. This is something we are currently working on, although the beta for this is currently running, and a general availability should be out soon. So what does containerized Spectrum Scale mean? This, in its core, it means that a set of pods are running on all worker nodes that actually load the kernel extensions and start the file system daemon. So this scale daemon is being run as a daemon set pods. These pods, however, need some special privileges to access and load kernel modules, to access and even mount the file system, or to have access to block devices and the host network. So at this point, these pods need to be privileged pods. Other services that are required for this entire solution to work, to provide persistent storage and to provide management capabilities, REST API, GUI, performance data collection, etc., they are run in separate containers. And deployment of this entire containerized scale is managed through operators. Now, in this release, or in this first delivery, the deployment mechanism that is being supported is via cross-cluster mounts, wherein the actual storage will come from a traditional Spectrum Scale storage itself. You will need to have a storage cluster which is a separate traditional Spectrum Scale storage or an ESS storage, which is then remotely mounted on the containerized spectrum scale cluster deployed on an OpenShift environment. So the spectrum scale cluster on OpenShift is going to be your compute cluster cross-mounting the storage from remote cluster. This in turn will actually work with the Scale CSI driver to provide the persistent storage for your application containers. Now, this entire mechanism of remotely mounting the cluster, deploying the spectrum scale on your OpenShift cluster is being managed through the operators. And this will be able to run, or this will run on the core OS. There is no need to install RHEL worker nodes on the OpenShift cluster. So with this, we will be able to support Power NZ on OpenShift clusters as well. As I mentioned before, the beta for this is already running, and it should be generically available later this year. So if we have time now, I'd like to show a brief demo of the Spectrum Scale CSI driver and how it is deployed using operators and how you can provision volumes using the CSI driver.
This video shows how IBM Storage Solutions supports Red Hat OpenShift workloads. IBM Spectrum Scale is a highly scalable, high-performance unified storage for files and objects. Thanks to CSI driver, it can also welcomes containers. We first need to deploy the CSI driver in the Red Hat OpenShift container platform. The IBM Spectrum Scale CSI driver is available as a plugin operator in the OpenShift catalog. OpenShift can claim directly permanent storage. You can choose in which class your storage will be provisioned. In a few seconds, your file set is provisioned with a unique ID. On the Spectrum Scale interface, you can recognize the file set with the same ID. The size is defined by a quota. We can deploy an application using this persistent volume claim. As an example, a WordPress application is installed on this storage. Spectrum Scale offers read-write many mode capability. It means that we can scale dynamically the number of instances of WordPress sharing the same file set. Thanks for watching this video. You can visit the full demo.
All right, so this is what we had for the Spectrum Scale CSI driver. We can take any questions now.
Yes, Rena, Smita, a question about what's coming next in the normal implementation of CSI. We are currently on 2.0.0, and when comes 2.1 or in sub-release? Are there any infos on that?
So 2.1 should come by the end of this year, in fact, in November. And there are improvements in terms of support for node taint tolerations is added, and power support is going to be there. In the next year's release, we are going to release additional features like snapshot support whenever Kubernetes GAs it. Currently, snapshot is not a GA function in Kubernetes. So whenever Kubernetes is ready to GA it, we will be GAing that feature.
All right. Well, thank you very much to our speakers. I'm sure they'll hang around for, if there are any additional questions in the chat, in the Q&A window or whatnot. I did post the URL for the Spectrum Scale user group in the chat window, so you can get a look. There's recordings from past events and also a calendar of future events. Our next event is on October 21st on managing the life cycle of your files using the policy engine. So, yeah, with that, thank you again very much and goodbye.